Modern high-performance aircraft require electric gyroscopic instruments. The turn and slip indicator, the attitude indicator, and the directional gyro. These electric instruments are dependable at extremely low pressures and temperatures, where gyrosuction instruments are unreliable. This film will explain the theory of operation of some of the newer electric gyroscopic instruments. To understand any gyroscopic instrument, you must understand the principle of the gyroscope. It consists of a rotor mounted in a gimbal. The rotor can spin in one plane only. When another gimbal is added, a second plane of movement is possible. And when this assembly is mounted in bearings, the rotor has 3 planes of movement and can assume any possible attitude. This is now a freely mounted gyroscope. A spinning gyro has 2 important properties: precession and rigidity in space. All of its practical applications are based on these 2 properties. As for rigidity in space, the spinning rotor remains in its original attitude, while the gimbals and base move around it. In other words, the gyro maintains its axis in relation to space and not to the surface of the Earth. If a gyro moves around the Earth, its axis is vertical to the Earth's surface here, at an angle here, and horizontal here. The gyro will resist any force that attempts to change its plane of rotation. This leads to the principle of precession. When a downward force is applied here, the gyro moves, but not in the direction of the applied force. Instead, it moves at right angles to the applied force. This action is known as precession. If an upward force is applied at the same place, the gyro again precesses at right angles, but in the opposite direction. The explanation is simple. The rotor is spinning in this direction. When the force is applied, the gyro precesses in a direction to align the direction of rotation with the direction of the applied force. The rate of precession is in direct proportion to the applied force. Small force, slow precession. Greater force, faster precession. If enough force is applied, the gyro precesses a full 90 degrees. However, at or near 90 degrees, it will tumble and go out of control. This disadvantage must be overcome in gyro instruments. Another disadvantage comes from the gyro's tendency to drift away from its original attitude. There are 2 types of drift. One is mechanical, due to friction in the bearings. This is actually a form of precession. The other type, known as apparent drift, relates to rigidity in space. Once again, consider this condition. The gyro maintains its attitude while the Earth turns under it. Every 6 hours, the gyro drifts through 90 degrees in relation to the Earth's surface. In order for the gyro instrument to be dependable, drift must be corrected continuously. There are several types of erection systems that correct for drift. The principle back of all these systems is based on 3 steps. The direction and degree of drift are measured by electrical or mechanical sensing elements. These elements then control the application of a proper force to the gyro, and it precesses back to its normal attitude. All gyros in this film are actually the rotors of electric motors. However, for simplicity, we will represent them like this, this, and this. We will start with the turn and slip indicator. It is really 2 instruments, each of which provides the pilot with information during a turn. This needle shows how much the aircraft is turning. This ball shows the kind of turn the aircraft is making. We will examine the turn needle first. It is actuated by a gyro, which is mounted in only one gimbal and in bearings that are secured to the case. The gyro can turn about the fore and aft axis, but not about the vertical axis. A spring restrains any movement of the gyro from its normal attitude. The gyro is linked to the turn needle like this. We will see how the property of precession is used to indicate the aircraft's rate of turn. When the aircraft turns to the right, forces are applied at the gyro bearings here and here. The rotor is spinning in this direction, so the forces cause it to precess in this direction. The linkage moves the needle in the direction of the turn. When the force of precession equals the spring tension, the needle indicates the rate of turn, as well as the direction. When the aircraft levels off, the spring erects the gyro to its normal attitude, and the needle returns to zero. A dampening piston and cylinder are linked to the gyro to steady any precession and prevent hunting by the needle. The ball is independent of the gyro. It is free to move back and forth in a curved tube. During straight and level flight, the force of gravity holds the ball in the center of the tube, and the aircraft is in balanced flight. During a turn, two additional forces affect the ball: horizontal lift and centrifugal force. When these two forces are equal, the aircraft is in a balanced turn, and the ball remains in the center of the tube. When the centrifugal force exceeds the horizontal lift, the aircraft skids, and the ball rolls toward the outside of the turn. When the horizontal lift exceeds the centrifugal force, the aircraft slips, and the ball rolls toward the inside of the turn. We will examine two attitude indicators, the H6 horizon indicator and the vertical gyro indicator. Each instrument continuously indicates the roll and pitch attitudes of the aircraft in relation to the actual horizon, and each obtains this information from a freely mounted gyro. The axis of the rotor is vertical and, due to the property of rigidity, will remain in this position as the aircraft assumes any attitude. Therefore, the gyro establishes a vertical reference from which roll and pitch deviations of the aircraft can be measured. It is unnecessary to cage the gyro in either instrument during any maneuvers. We will start with this one. This miniature plane represents the aircraft, and this bar represents the horizon. The horizon bar is mechanically linked to a gyro mounted in the case. The two supporting arms are connected to pivots at the rear of the outer gimbal and by pins to the inner gimbal. When the aircraft climbs, the gyro remains erect, while the aircraft and case move around it. This action lowers the horizon bar below the miniature plane. The instrument now indicates the aircraft's present attitude relative to the horizon. At plus or minus 27 degrees of pitch, the horizon bar reaches mechanical stops and ceases to give any further indication of pitch up or down. Some models of this instrument have a scale to indicate pitch to 80 degrees plus or minus. In addition to the horizon bar, this pointer is secured to the outer gimbal of the gyro. It is used with these fixed markings on the case to indicate the degree of roll. When the aircraft rolls, the gyro remains erect and holds the pointer in this position, while the horizon markings roll around it. The degree of roll can be read here. The pilot can use these knobs to adjust the positions of the miniature plane and horizon bar manually. Since the gyro is linked mechanically to the horizon bar and pointer, the dial must be mounted in a vertical position. This model of the attitude indicator has a fixed miniature plane and roll markings on the instrument face. Back of the dial face is a sphere representing Earth, sky, and horizon, with 5-degree markings for climb and dive. It is universally mounted, so it can rotate around this axis 82 degrees in either direction, and can roll 360 degrees around this axis. This pointer can move only around the roll axis. A remotely mounted gyro controls the sphere through 2 electric circuits, one for roll, the other for pitch. A position transmitter is in the roll axis of the gyro, and another is in the pitch axis. They connect through receivers and amplifiers to the servo motors that drive the sphere in pitch and roll. Assume the aircraft rolls 30 degrees. This transmitter measures the roll displacement of the aircraft from the vertical reference. This measurement, in terms of a small voltage, goes through the receiver and amplifier to the roll servo motor, which turns to position the sphere and pointer. The degree of roll is indicated by the pointer and roll markings. Assume the aircraft climbs at a 30-degree angle. This transmitter measures the angular motion in terms of a voltage. The amplified voltage drives the pitch servo motor, which turns to position the sphere. The degree of pitch can be read on the horizontal markings back of the miniature plane. When the aircraft reaches 82 degrees of pitch, the gyro goes through a controlled precession of exactly 180 degrees. As a result, the sphere also exactly reverses its position and continues to indicate the aircraft's changing attitude. This knob can be used to position the sphere electrically. The dial can be installed at any angle because the gyro is not mounted in the instrument case. We will examine 2 directional compasses, the C1 Directional Gyro Heading Indicator and the MA1 compass system. And we'll start with this one. The aircraft's heading is indicated here, and the reciprocal heading here. To obtain this information, the instrument uses a freely mounted gyro. Due to its property of rigidity, the spin axis of the gyro will hold its attitude as the aircraft and instrument case turn about it. Secured to the outer gimbal is a gear. Its teeth mesh with the teeth of another gear, to which the compass card is attached. Before it can indicate correct headings, the compass card must be set to the heading of the aircraft, as indicated by the magnetic compass. The push-to-cage knob is used to make the setting, after which the gyro controls the compass card. Assume the aircraft makes a 90-degree turn. The instrument case turns around the gyro and lower gear. As a result, the vertical gear makes a quarter turn as it travels around the lower gear. So the compass card also makes a 90-degree turn. Any climb or descent will not affect the compass card unless the heading changes. However, if the pitch or roll of the aircraft exceeds 60 degrees, the gyro will tumble and may be damaged, and the instrument will give inaccurate readings. Therefore, when entering a maneuver that may exceed the limitations, the gyro must be caged. The instrument will be safe, but out of operation. When the maneuver has been completed, the magnetic compass heading must be set into the instrument again. In this instrument, apparent drift causes the compass card to drift away from its heading about 3 degrees every 15 minutes. And so, every 15 minutes, it must be reset to the magnetic compass heading. We have seen that a gyro is stable and accurate for short periods of time, but is subject to long-period drift. In contrast, a magnetic compass is accurate over long periods, but subject to short-period instability and oscillations. The magnetic compass is particularly accurate between 60 degrees north and south latitudes. But near either of the poles, the dip angle of the Earth's magnetic lines of force causes this compass to become unstable. The MA1 compass system combines these two instruments into one system that uses their advantages and eliminates their disadvantages. The magnetic compass, in the form of a flux valve, is mounted remotely in the tail or wingtip, away from the worst magnetic disturbances within the aircraft. The gyro is also mounted remotely from the indicator dial. The system is designed for two modes of operation. In the free gyro mode, the gyro alone controls the indicator dial. In the slaved mode, the magnetic compass controls the gyro. We will first examine the slaved mode of operation. We will represent the flux valve as a magnetic needle mounted on the rotor of a synchro transmitter. The needle will remain aligned with the Earth's magnetic field while the aircraft turns in any direction. The stator of the compass transmitter is connected electrically to the stator of a synchro control transformer. The gyro's outer gimbal is mounted on the rotor of this synchro. When the outer gimbal is properly oriented to the magnetic needle, there is zero output from the control transformer. But if the aircraft changes heading or the gyro drifts around the vertical axis, the outer gimbal is not properly oriented. The control transformer immediately sends an error signal through an amplifier to the torque motor mounted on the inner gimbal. The torque motor applies the proper torque to the inner gimbal, and the outer gimbal precesses to proper orientation with the magnetic needle, at which time the error signal is canceled. The magnetic needle may oscillate and send an oscillating signal to the gyro. However, the gyro's rigidity in space is such that it does not respond quickly to slight changes in the needle. Instead, it aligns itself with the average position of the needle. Mounted above the gyro is a synchro transmitter, which continuously measures the deviation of the gyro case from the outer gimbal. It transmits this information to the indicator dial, where another synchro positions the compass card to indicate the aircraft's heading. Thus, in the slaved mode of operation, the gyro is a drift-free, stable indicator of magnetic direction. In the free gyro mode, the flux valve is disconnected from the gyro. When the gyro is oriented properly, it tends to hold that orientation. However, it is subject to apparent drift, which increases as the gyro approaches one of the poles. Apparent drift is corrected automatically by latitude compensation circuit. The aircraft's latitude is set manually into the system and changed whenever necessary. This sends an appropriate and constant voltage to this torque motor. The motor applies a constant torque to the inner gimbal. As a result, the outer gimbal precesses constantly at a given rate to offset the apparent drift, and the gyro sends accurate directional information to the indicator dial. Electric gyroscopic instruments are dependable at the low atmospheric pressures and temperatures in which modern high-performance aircraft must operate.